Today we're going to talk about section 8.1, which is solving systems algebraically. This should be review. You've done this in both Algebra 1 and Algebra 2, so hopefully we can just brush up on some things and make sure we've got it all. Remember, however many variables you have, then that's how many equations you need to be able to solve it. So if you just have x and y or two variables, then we need two equations to be able to solve it. A consistent system of equations has a solution. An inconsistent system has no solution. When you go to solve these, it won't work out no matter what you do. An independent system has a unique solution, and a dependent system has infinitely many solutions. When you solve a dependent system, you'll end up getting something like a number equals itself. Like you'll get 6 equals 6. Well, that doesn't really tell you anything. So what that tells you, though, is that there are infinitely many solutions. No matter what your variables are, then they still will work out. Now, when you have systems of equations, the thing you need to remember is that all equations have pictures, the graphs that we looked at. And when you have a system of equation, the solution is where the graphs intersect. So if you have two lines, it's where those two lines intersect. Or if you have three planes, which would be with x, y, and z in the equation, then it's where the three planes intersect. But your solution is always where those pictures intersect. Because remember, the picture, the graph, is a picture of all the different solutions for that one equation. So if you want a picture of two equations, what solves both of them, it's where they intersect. There are two methods that we use for solving these so far. We use substitution, where you solve one of your equations for one variable and then plug it into the other equation. Usually we use substitution only when we just have two variables and two equations, because it gets a little more complicated with the bigger systems. Elimination, or sometimes called the addition method, we use several times with both double systems and with more complex systems, so that we can eliminate one of the variables by adding two of the equations together. That we should know how to do those, so we'll review some just to make sure we know how to do that. So let's look at an example so we can review this. Let's say we have a system of equations, and we just have two variables, so that means we need two equations if we want to be able to solve them. Now there's nothing really you can eliminate. You can't add these together or multiply something easily so it adds together easily. So it looks like substitution is going to be a better method. So let's take this one and solve it for x. So if we add 4y to both sides, we get 3x equals 4y plus 9, and then divide by 3 and we get x equals 3 plus 4/3 y. So here's our equation. We just took this first one, solved it for x. Basic algebra stuff. So now we can take this and plug it in over here. So we have 7 times our x. Now we only have y. So we know how to solve this equation. It's just got one variable. So we multiply this out. And I'm going to go ahead and change this into a thirds fraction so that I can have a common denominator. So if I subtract 21 over here, I end up with -5. And if I subtract those two, I get -5/3 y. So what I want to do is multiply both sides by -3/5 so that I can solve for y, and I get y equals 3. Well, now that I have y equals 3, I can plug that back in here, and I'll have x equals 3 plus 4/3 times 3, so those cancel, and I get x equals 7. So that means my solution is 7, 3, because remember, points go x, y. And what is this? This is the point where these two lines intersect. So let's look at these. If we solve both of these for y, we get y, the top one, we'll call it y1, equals 3/4 x minus 9/4. And then the second one is 7/11 x minus 16/11. And I trust that you know how to take these equations and solve each of them for y. So if we have these two, we can use that and we can look at our graph. So let's look at our calculator. And if we want to do this, we need to, let's see here, we need to type in our equations. So we've got 3/4 x minus 9/4 and 7/11 x minus 16/11. Okay, so you should have in your calculator typed in these two equations. Now, once you have these two equations, we'll just put them in a standard window. See if we can get this to work. Sorry, you guys know how sometimes it decides to mess up on us. All right, so now we have this graph. We have two lines. Now over here it looks like that's where they're intersecting. So let's kind of zoom into that. So we're going to change our window so we're just looking at the first quadrant. So change your x-min and your y-min to 0. And it's going to do it again. Actually, let's see. Let me adjust my window a little bit here and get it working, and then we'll see if we can get it to cooperate with us. So work on your calculator and get your picture and zoom in on where it looks like it's intersecting. So it should be, we found that it was this 0.73, so it should be over in that direction. So zoom in there, and just 1 second and I'll show it to you. Okay, so we've got this intersection here. Now on your calculator, you can actually have the calculator calculate it for you. Let's see if we can get it to do this without messing up. If you do second calc and you go where it says intersect, number 5, and it asks you which curve you want, and you look at the top left, it says y1, yes, that's the one we want, so we hit enter. And y2, yes, that's the second curve we want, so we hit enter. And then we made a guess, we just move our cursor over sort of near where we think they're intersecting. And we hit enter, and we get that our intersection is at 7,3. So you can see that calculating it out algebraically, what we're getting is a picture of, what we're getting is the numbers to go with the picture for these graphs. So that we have 7,3 is that point that's on both graphs. So that's the solution to the system. All right. Now, obviously with planes and such, it's harder to do that, and you can't really draw those or graph those on your calculator or anything. So we're going to solve the systems algebraically more often than not. But when you have two systems, you can check yourself by using the calculator. So let's look at a different one. Sometimes we're going to have a little bit of a different scenario where we're going to have to alter it a little bit. Now, we have an equation with two variables, but it looks pretty complicated, more difficult to solve. Well, it's really not, because what we can do is we can say A is 1 over X and B is 1 over Y, and now all we have to do is solve a system just like we know how to do. Sorry. So we have our system like this. So now here we've got, it's in A and B, and once we solve A and B, then we'll know what X and Y are. This is a perfect example of one that would work for elimination, because you see here the A's, we've got 3 and 6. Well, if we multiply 3 times -2, then we'll get -6, and that will eliminate. So what we need to do, remember, you have to do something to the whole equation. So what we end up with is -6a plus 10b equals 1/6. And then our other equation just stays the same. And this should be, hopefully this is review. So when you add it up, these cancel. -6a plus 6a is 0, so those go away. And we have 13b equals 26 over 30. Remember, get a common denominator, so this is 5 over 30, and this is 21 over 30. So then we divide both sides by 13. So that's the same as multiplying times 1 over 13. And cancel, and we get b equals 1 over 15. So when b is 1 over 15, that means that we can plug it back in over here, and we have 6a plus 3 times 1 over 15 equals 7 over 10. So this cancels, we get 5 and 1. I'm just running through the algebra here really quickly. If you're having trouble with it, make sure you slow down and pause and rework it, because this should be review, and if you're having trouble with it, you need to make sure you come see me. So if we subtract the 1/5, we get 6a equals 1/2, which means a is 1/12. So now we have a is 1/12 and b is 1/15. Well, what does that mean x and y are? Well, since x is just the reciprocal of a and y is the reciprocal of b, that means x is 12 and y is 15. So our answer is 12, 15. This is the point where these two lines intersect, or where these two graphs intersect. So if you have two variables, you need two equations, you can either use substitution or you can use elimination, and you can solve it out. And if you have to play around with it a little bit to make it look nicer so that you can work with it, then do so. Now, sometimes it's a little more complicated because we have 3 equations. So let's say we have this. So these are graphs of planes. So what we're looking for is the point XYZ where all 3 planes meet in space. Now, substitution is harder when you have 3 variables. So we use elimination. If you want to try substitution, that's fine. Solve one of them for one of the variables and then plug it in so that you just have 2 variables, and then you can solve however you need with the 2 variables. Personally, I like elimination better, especially when I have things like this right here. See this -2y and this +2y? That is really easy to add together and get 0. So the first thing I'm going to do is use that. So I'll take these first 2 equations. Having all kinds of technical difficulties today. Sorry, guys. All right, so when we add these 2 together, we have 12x and then 0y and plus 2z equals -4. So now we just have an equation in x and z. So now I look at these, I used the first and second, so let's look at the second and third. Is there another way I can get rid of y with those? Well, this is a little harder, but not impossible by any stretch. So let's write those down. So we have 7x plus 2y minus z equals negative 5, and 2x plus 3y minus z equals 3. Now, the reason I want to get rid of y is because I already did for this one, and then I'll have a system of two equations with two variables, and they'll be the same ones, and I can solve that just like I did with my other ones and work backwards to get all the variables. So I want to make sure I'm eliminating the same variable both times. So if I multiply this one through by 3 and this one through by negative 2, then I'm going to end up with 6y and negative 6y, which will be 0, and that gets rid of it like I want. So here, 3 times 7 is 21, minus 4x gives me 17x. 6y minus 6y is 0. Negative 3z plus 2z is minus z equals, and then negative 15 minus 6 is negative 21. All right, pause it and make sure you're absolutely positive you know how we got all of this. All right, so now we have two equations with two variables. We know how to do that. Let's set them on top here of each other. Now, here we've got this plus 2z and minus z. So I can eliminate again by multiplying this one through by 2. So I have 12 plus 34, which is 46x. And then I have 2z minus 2z, which is 0, which is what I wanted. Then I have negative 4 minus 42, so that's negative 46. So divide by 46, and I get x equals negative 1. So there's one of them. Then I can plug that in here, and I have negative 17 minus z equals negative 21. If I add 17 over here, then I end up with negative 4 divided by negative 1, and I get z equals 4. Well, now I have two variables solved for, x and z. So let's take both of those back up here to this first equation. You can use any of them, but I just picked the first one. So we get negative 5 minus 2y plus 12 equals 1. So negative 5 plus 12 is 7. Subtract the 7 over here. I get negative 2y equals negative 6. So that means y equals 3. So my solution is negative 1, comma 3, comma 4. Remember, x, y, z. Now, we went through this pretty fast. You need to make sure you pause, go back and pause things and work things out and make sure you remember all this, because while it should be review, it may not be. And you need to make sure that you know how to do this because we're going to use it in this chapter a lot. So read the section, go back over this a couple of times, and make sure you've got this down.